What's up, AP Chemistry people? We're going to do some demo stuff to start with here. So I have some iron in here, right? So the thought process for our next unit has a lot to do with charges and what charges things have and changing charges and all that kind of stuff. So we're going to talk about oxidation states a little bit today, and then changing those oxidation states and stuff, and figuring out what the oxidation state is. So an oxidation state is just bookkeeping of electrons and that kind of stuff. It can be a real charge that something has, or it can be kind of just how we assign where the electrons are in more covalent type things. So question of the day to start with: what is the charge? What is the oxidation state of this iron? I'm sorry, I didn't hear you. What do you think? You got to answer. You got to have a choice. Did you say +3? No, that's the most common charge on iron, but the charge on this iron is not +3. Did you say +2 because of my shirt? No, that's ferrum or ferrous. Sorry, ferrous. As in Ferris wheel, right? Get it? Ferris wheel, because it's a wheel and it's Ferris, right? So nerds be nerding. So no, this iron is elemental iron. So the charge on this iron is 0. It doesn't have a charge. So when you hear something like, what's the charge on this magnesium? What's the charge on this sodium? Don't always go to what's the common charge on it, right? When it reacts. If it's in its elemental state, the charge is 0. Now we can change that. If I react this iron, lower our screen down just a little bit here. If I react this iron, in fact, let's get with either maybe an acid or a flame or something like this, right? Then we can get the charge to change. So if we sprinkle a little bit of our iron into the flame, right? Like sparklery, like sparklers kind of thing, right? It'll ignite, and then that iron, right? The iron that we're seeing react, that is changing charge. That is getting a combination of some of it'll be +2, some of it'll be +3. Kind of just depends on how the electrons are arranged. The +3 is the more stable state. We'd have to gather it and do some more testing to figure out what charges it has. But something to keep in mind, a common mistake that a lot of people will make, especially with something more like magnesium, that you're like, oh yeah, +2. Well, not if it's the magnesium strips. I was going to do this with magnesium strips, but I'm out for the year. And so I'm not going to order more. We'll just do that with iron. And that worked out because of my iron shirt today. So we're going to look at oxidation states and stuff today and get some notes in. So we are in our last unit here, electrochemistry. Basically, we're going to look at redox reactions. I've got some iron all over my hands from the burning that iron. Redox reactions. How do we, reminding ourselves on the oxidizing agents and reducing agents, and keeping track of electrons as those take place. Really, if you look at chemistry at its most fundamental level, pretty much everything is some sort of acid base or redox, right? When we think about combustion or burning stuff, well, that's really redox. When we think about iron rusting and single replacement reactions and that kind of stuff, well, that's all single replacement reactions. When we think about all the battery stuff, that's all redox reactions. So synthesis, decomposition, most all of those are all redox reactions. If it's not redox, it's pretty much acid base. That's really the most fundamental way to do it. Not the most helpful way for like a first year chemistry student, but when you look at the real truly what's going on, that's kind of what's going on in most of those. So we're going to look at oxidation states. Then we're going to spend a good bit of time balancing redox reactions, which is a different way to balance equations, which is very weird the first few you do. But after you do a few of them, it actually is pretty slick, and most students have a lot of success with it. And then battery stuff, basically electrochemical cells, how do batteries work, and all that kind of stuff. So jumping into it here, electrochemistry. Big idea here is we've got to be able to figure out what the charge is on stuff. I would write these rules out. They are also available in your book, but I would write them all out. Elements are going to be 0. Keep that in mind, especially when we see things that we're used to seeing like oxygen and sodium. If it just says sodium, that's an element. Don't go, +1 and move on, right? Unless it's got a charge or it's in a compound, it's just 0. Compounds are going to add up to 0. So when we see something weird like this and you're like, well, what's the charge on chlorine? -1. No, that's the common charge on chlorine. But if we look at this one, we know oxygen is going to be -2. So that's a total of -8. We know hydrogen is going to be +1. So that means your chlorine must be a +7, right? Which is not the normal thing for chlorine. But if you start counting, it does have 7 valence electrons. +7 is a charge that can make some sense for us on that. right? The bold things here are kind of our rules, right? Any one atom ion is going to be equal to its charge. So if it's an Na +1, well, that's just going to be a +1, duh. Alkali metals are always going to be +1 when they're in compounds. Fluorine is always going to be -1 when it's in a compound. So if I look at something that's not so obvious, like a Bf2-, well, now I know I've got two -1s, and I've got a borine. I just made up a new element. That is not the most exciting element in the world. So I've got a -1 and a -1, so that's a total of -2. And then my boron must be balancing it out so that overall it's a -1, so my boron must only be +1, right? So that's, but I know fluorine, a good rule, fluorine is going to be -1 if it's in a compound, just like alkali metals are going to be +1. The other halogens, not so straightforward. They like to be +1, but they're not always +1. Your alkaline earth metals are always going to be +2. And then aluminum and gallium are pretty much always going to be +3. I've seen a couple rare instances when gallium wasn't a +3, but you can pretty much count on it being a +3. Hydrogen's going to be a +1 unless, now you start to get to the unlesses. Hydrogen's going to be a +1 unless it's with a metal. Then it's going to be a hydride where you've got like lithium and hydrogen. You're going to list it second. So it's not the first one listed. So it's listed where the anion is. You'll call it a hydride, like lithium hydride, sodium hydride, calcium hydride, that kind of thing. They tend to be pretty reactive because sodium doesn't love to be this -1. But hydrogen's usually going to be +1 in a compound. Oxygen is usually going to be a -2 unless it's a peroxide. You kind of recognize peroxides because they're going to be with somebody like potassium and be weird, or a superoxide or something like that. But unless oxygen is in a peroxide kind of thing, it's going to be a -2. When it's a peroxide, it's only -1. So when we look at something like H3PO4, I've got -8 for my oxygens. I have +3 for my hydrogens. So that all adds up to a -5. Overall, that's a compound, so my phosphorus must be a +5. Hey, again, +5 is not what we usually see for phosphorus, but that is a charge that does make some sense for phosphorus. It has 5 valence electrons. It could lose those, especially as somebody more electronegative like oxygen. Right, I know I went through those rules pretty fast, but you can go back through and write those down, put me on pause and write those down as slow as you want. Oxidation reactions are going to be ones that involve moving an electron. So remember, we say Leo says Gur. We never say oil rig because that's for stupid people. We don't like stupid people. We only like Leo says Gur. That is the only one we ever use. Leo is lose electrons oxidation. Gur is gain electrons reduction, reduces the charge kind of thing. So when we look at zinc, zinc is going from no charge to +2. So how is it going to do that? How is it going to go from no charge to +2? Dora the Explorer time. How's it going to happen? That's right. It's going to lose electrons. In order to go from no charge to +2, it has to lose electrons. And I know you said it's going to lose electrons because I heard you say it, right? I heard you say that. And so when it loses electrons, it is oxidized. So zinc is being oxidized here. Notice there is no oxygen in here. When we first talked redox, hundreds of years ago, they thought it had to do with oxygen. Oxygen is very often involved with these things, but not always. We know now at a more fundamental level, it's about the electrons. Biology still tends to focus on the oxygens a lot because there's pretty much always oxygen there in biological reactions. But chemistry is looking at it from a more puristic standpoint kind of thing, right? So if zinc is being oxidized, well, I know hydrogen better be being reduced. So I should be able to figure out that hydrogen is gaining electrons. So I see hydrogen with a plus charge here, and then over here, hydrogen has no charge. Well, it went from a plus to a no charge, so that must be gaining electrons, right? There's a partnership there, just like an acid-base. There can't be an acid without a base. Well, there can't be a reaction, right? Well, there can't be something that is being oxidized without something that is being reduced. If we jump to our agents, then an agent is something that forces something else to happen. So since zinc was oxidized, it was causing something else to be reduced. So zinc is your reducing agent. Hydrogen is your hydrogen ion. Here is your oxidizing agent. No, the reactant there, not the H2. The H plus is your oxidizing agent. It caused somebody else to be oxidized because it was reduced. It's just easy to get that backwards in your head at the beginning. So here's that all written out, right, as a reminder. So when we look at the old school rechargeable batteries, right? These were the original ones. They did not last but a few years. We have a lot better ones now. There are still some of these, but they've started to make those a little better, and they're kind of starting to get phased out. Not as much Nicad batteries. When you hear the term Nicad, if you look at rechargeable batteries, some of them will say Nicad on them. That is nickel cadmium. So we look through here. So good idea to put me on pause for a second and figure out all the stuffs. But I'm going to go ahead and work through this. Cadmium has no charge here. First off, let's back up a step. Who do I know who to look at here, right? So number one, I'm going to look at anybody who's an element who on the other side is not an element, because I know they change charge. So that's going to be pretty easy. Number two, I'm going to look at my transition metals that are involved, because transition metals are pretty easy to change charges on. I'm going to look at, then I'm going to look at P block elements other than oxygen, like your phosphoruses, your chlorine, stuff like that, because those are pretty likely to change charge. But usually in one of those three, you're finding somebody who's changed charge. And carbon, another good example, one that changes charge all the time. So cadmium has no charge here. Over here, it has what appears to be a +2 charge, right? Because hydroxide is -1, so this must be +2. So cadmium went from 0 to +2, so that means it lost electrons. So if it lost electrons, it was oxidized. If it was oxidized, then it forced somebody else to get reduced. So cadmium, Cd, is your reducing agent. Not CdOH2, but cadmium is your reducing agent because it forced somebody else to be oxidized. When I look through the rest of these, I figure nickel is probably my next most obvious choice to change. Nickel here is +4. I have no reason to think that's a peroxide. If they wanted this to be a peroxide, they would need to let me know. I'm going to assume this is nickel 4 oxide. So nickel 4 oxide with a nickel having a +4 charge. Over here, this must be nickel 2 hydroxide. So nickel went from +4 to +2. So if it went from +4 to +2, then it gained electrons. So it was reduced. So if it was reduced, then it is the oxidizing agent, right? We can kind of recognize those things. Okay, we will start practicing balancing redox tomorrow. It is one of the more fun things that we get to. I really enjoy that. So we'll do that tomorrow. Hopefully this helps. Start looking through reading the chapter in the book and that kind of stuff at this point too. Let me know if you've got questions.